Before we dive in, one honest correction on the timing because it actually matters for understanding this story properly. These images weren't released 6 minutes ago. They were unveiled on June 23rd, 2025 at an event in Washington, D.C., broadcast to hundreds of watch parties held around the world simultaneously. That's not a knock against how significant this moment was. It absolutely was significant, arguably one of the biggest astronomy stories of the decade. It's just that the real version of this story doesn't need a fake sense of breaking urgency to be worth your full attention. So let's walk through what actually happened, why astronomers everywhere were genuinely, legitimately blown away, and why this single observatory is about to fundamentally reshape how humanity studies the universe for the next decade. The facility at the center of this story is the Vera C. Rubin Observatory, a joint project of the U.S. National Science Foundation and the Department of Energy, sitting atop Cerro Pachon, a mountain rising roughly 5,200 feet above sea level in the Chilean Andes, chosen specifically for its exceptionally dark skies and stable atmospheric conditions, ideal for the kind of deep, wide-field astronomical survey work the observatory was built to perform. It's named after Vera Rubin, the American astronomer whose meticulous observations of galaxy rotation in the 1970s provided some of the first strong evidence for the existence of dark matter, a fitting namesake, since the observatory's primary scientific mission over the coming decade centers directly on studying dark matter and dark energy, the two mysterious phenomena that together are believed to make up roughly 95% of everything in the universe, while remaining almost completely invisible to direct observation. At the heart of the observatory sits the Simonyi survey telescope, an 8.4-meter telescope paired with the LSST camera, the largest digital camera ever built for astronomy, a genuinely staggering piece of engineering weighing about as much as a small car and capturing images at a resolution of 3,200 megapixels. To put that number in perspective, if you wanted to display one single full-resolution image from this camera at its actual native size, you would need roughly 400 separate 4K television screens arranged together just to show that one picture in full detail. Each individual image the telescope captures covers an area of sky equivalent to 45 full moons placed side by side, or about 9.6 square degrees. An extraordinarily wide field of view for a telescope, with this level of light-gathering power and precision, a combination that, according to the observatory's own team, no other telescope on Earth currently matches. When the first images were finally revealed to the public on that June day in 2025, they didn't disappoint. One of the standout images, which the observatory team nicknamed the Cosmic Treasure Chest, is a composite of the Trifid and Lagoon nebulae, two popular visually striking star-forming regions located several thousand light-years from Earth, favorite targets for astronomers and amateur stargazers alike because of their dramatic, colorful clouds of gas and dust. What made Rubin's version of these familiar objects so remarkable wasn't that nobody had ever photographed them before. It's that the image was built by combining 678 separate exposures, captured in just 7.2 hours of total observing time, stitched together into a single composite containing roughly 2 trillion pixels of data. That combination of speed and depth is precisely what sets Rubin apart from essentially every other observatory currently in operation. No other facility on the planet can produce an image this wide, this detailed, and this deep, in the short span of observing time, a genuinely unique capability rather than simply an incremental improvement over existing telescopes. But the nebula image, stunning as it is, wasn't even the most scientifically significant result from that first release. In just over 10 hours of test observations, well before the observatory's main 10-year survey mission had even officially begun, Rubin had already captured images containing an estimated 10 million galaxies, along with millions of individual Milky Way stars and thousands of asteroids within our own solar system. An almost unbelievable volume of astronomical data gathered during what was still, technically, a testing and calibration phase, rather than genuine, full-scale scientific operations. Yusra Al-Sayyad, a Princeton University researcher who oversees image processing for the observatory, captured the significance of this shift plainly, pointing out that astronomy, up until this point, has mostly given us snapshots, individual images capturing single moments in cosmic time, while Rubin's real, defining purpose is to build something considerably more ambitious. Essentially a movie of the universe, allowing scientists to watch cosmic events unfold dynamically over time, rather than working from isolated, disconnected still images. That dynamic, movie-like approach is really the key to understanding why Rubin represents such a genuine leap forward, rather than simply a bigger, more expensive version of an existing telescope. Once its main 10-year survey, officially called the Legacy Survey of Space and Time, or LSST, gets fully underway, Rubin will scan the entire visible southern hemisphere sky roughly once every 3 to 4 nights, repeating this process continuously for a full decade. capturing approximately 1,000 images every single night, guided by an automated scheduling system that accounts for factors like weather conditions and specific scientific priorities. Because the telescope revisits the same patches of sky so frequently, its onboard software can automatically compare each new image against a carefully constructed template built from all of the observatory's previous observations of that exact same region. And whenever something changes, a star exploding, an asteroid moving, a distant galaxy flickering, the system can issue a public alert within minutes, made freely available to astronomers and even amateur enthusiasts anywhere in the world. That capability alone represents a genuinely new kind of astronomical infrastructure, less like a traditional telescope pointed carefully at one target at a time, and more like a continuously running planet-scale change detection system for the entire night sky, catching transient, fast-moving cosmic events that a more conventional, narrowly targeted telescope would likely miss entirely. It's worth spending real time on exactly what kinds of transient events this rapid repeat scanning approach is expected to catch, because the range is genuinely broad and touches on some of the most exciting open questions in modern astrophysics. Supernovae, the explosive deaths of massive stars, are visible for only a relatively brief window before fading, and catching one early, ideally within hours or days of the explosion beginning, gives astronomers a far richer opportunity to study the physics of the explosion itself, the elements it produces and disperses into space, and its effects on any surrounding material. Information that becomes progressively harder to recover the longer you wait to start observing. Rubin's combination of extremely wide field of view and frequent revisit rate makes it particularly well suited to catching supernovae at these earliest, most scientifically valuable stages, across a far larger swath of sky than more narrowly targeted supernova search programs have historically been able to cover. The observatory is also expected to dramatically expand our catalog of asteroids and comets within our own solar system, including, notably, potentially hazardous objects whose orbits could someday bring them close to Earth. Current estimates suggest Rubin's survey could identify millions of previously undetected asteroids over the course of its 10-year mission, a genuinely massive expansion of humanity's catalog of known solar system objects, and a capability with real, direct planetary defense implications. Since identifying a potentially dangerous asteroid years or decades before any possible close approach gives scientists and policymakers considerably more time to plan a response, compared to discovering such an object only shortly before any potential encounter. Then there's the observatory's central headline scientific mission, the one its namesake's own research first pointed toward decades ago: dark matter and dark energy. Rubin won't detect dark matter directly, since by definition it doesn't interact with light in any way current instruments can directly observe. Instead, astronomers will study its effects indirectly, primarily through something called gravitational lensing, the way massive concentrations of matter, including the invisible dark matter woven throughout and around galaxies, bend and distort the light from more distant background galaxies passing near them, creating subtle, measurable warping effects in how those background galaxies appear. Because Rubin will image such an enormous number of galaxies, that estimated 10 million captured in just the first 10 hours of test observations alone hints at the scale involved. Across such a wide swath of sky, repeated so many times over 10 full years, it will give astronomers an unprecedented statistical dataset for mapping out exactly how dark matter is distributed throughout the universe, and for tracking, with far greater precision than has previously been possible, exactly how dark energy, the mysterious force driving the universe's accelerating expansion, has behaved over cosmic time. It's worth pausing to genuinely appreciate just how significant a scientific undertaking this represents, both in terms of raw data scale and in terms of the sheer international collaborative effort involved in bringing it to life. Rubin Observatory's construction was a roughly 2-decade-long undertaking, involving contributions from research institutions across the world. Researchers and engineers from institutions including UC Santa Cruz, Princeton, the University of Washington, and the University of Arizona, among many others, contributed key components, with the University of Arizona's Imaging Technology Laboratory, alone manufacturing and delivering more than 100 science-grade imaging sensors, nearly half of the camera's entire imaging array. The total project cost came to roughly $810 million, a substantial public investment, jointly funded through the National Science Foundation and the Department of Energy's Office of Science, reflecting the scale of ambition behind this project from its earliest planning stages decades ago. Jelko Ivezic, the director of Rubin Observatory Construction, described the first imagery release as representing, in his words, the culmination of about 2 decades of dedication, innovation, and collaboration by a genuinely global team, language that reflects both the real scientific magnitude of the moment and the sheer sustained institutional effort required to reach it. The scale of data this observatory will eventually generate over its full 10-year mission is genuinely difficult to fully grasp using ordinary everyday comparisons. According to the observatory's own team, the total volume of data gathered during just the first single year of the main LSST survey will exceed the combined total of all optical astronomical data ever collected by every other telescope throughout the entire previous history of the field, a claim that sounds almost too large to be believable until you consider the underlying math. A camera this large, this fast, and this wide field, running essentially every clear night for a full decade, inevitably produces a genuinely unprecedented volume of raw observational data, one that will require entirely new categories of data processing, storage, and machine learning-assisted analysis tools just to make full scientific use of, since no team of human astronomers could realistically sift through that volume of imagery by hand in any reasonable time frame. There's also a genuinely exciting democratizing dimension to this story worth including, because it reflects something meaningfully different from how much of modern professional astronomy has traditionally operated. Rubin Observatory has partnered with Adler Planetarium's Zooniverse platform specifically to invite members of the public to participate directly in real, genuine scientific research, using actual Rubin data, continuing a broader citizen science tradition that has already produced real, published scientific discoveries in other astronomical survey projects over the years. Given the genuinely overwhelming scale of data Rubin is expected to generate, this kind of public participation isn't merely a nice educational gesture. It may become a genuinely necessary component of how the observatory's full scientific potential gets realized, since even the most sophisticated automated systems benefit enormously from having large numbers of human eyes helping to flag and classify unusual or ambiguous objects the software alone might overlook or misidentify. It's worth being clear and honest, in the interest of giving a complete, accurate picture, about exactly where the observatory's timeline actually stands as of today, since this is precisely the detail that gets lost when a real, significant scientific milestone from over a year ago gets recycled with a false "just happened" framing. The images released in June of 2025 represented what astronomers call first light imagery, essentially a proof of concept demonstration confirming the telescope and camera system were functioning correctly and could deliver on their promised capabilities, gathered during roughly 10 hours of test observations rather than the observatory's full ongoing scientific survey. Following that release, the observatory moved into its formal commissioning phase, with the main 10-year legacy survey of space and time expected to begin in full over subsequent months, meaning that, as of today, the observatory has likely been conducting genuine, sustained scientific survey operations for a meaningful stretch of time already, generating exactly the kind of steady, cumulative dataset its 10-year mission was always designed to produce, an ongoing, still unfolding scientific story, considerably richer than any single first images moment alone could capture, however genuinely spectacular that specific moment turned out to be. So here's the honest, complete version of this story, stripped of the fake urgency, but I'd argue no less exciting for it. In June of 2025, humanity got its first real look at what the most powerful wide-field survey telescope ever built is actually capable of, revealing 10 million galaxies captured in a matter of hours. A nebula image built from nearly 700 combined exposures containing 2 trillion pixels of data and a clear, working demonstration of a genuinely new kind of astronomical infrastructure, one built not to capture single, isolated snapshots of the universe, but to construct something closer to a continuous decade-long movie of the entire visible night sky. That moment absolutely did capture the world's attention, legitimately, without needing any exaggeration, drawing watch parties across the globe and coverage from major science outlets everywhere. It just happened over a year ago, not 6 minutes ago, and the real, ongoing story since then, an observatory now likely deep into its historic 10-year survey, steadily building the largest, richest astronomical dataset ever assembled, cataloging millions of asteroids, tracking supernovae in near real time, and mapping the invisible scaffolding of dark matter across the observable universe, is honestly a far more interesting, far more substantial story than any single dramatic headline moment could ever fully capture on its own. Let's spend some more time understanding exactly why Vera Rubin herself makes such a fitting namesake for this observatory, because her own scientific story adds a genuinely meaningful layer of context to everything Rubin Observatory is now trying to accomplish. Working in the 1960s and 1970s, at a time when women in astronomy faced substantial professional barriers, Rubin, alongside her collaborator Kent Ford, carefully measured the rotational speeds of stars orbiting within spiral galaxies, expecting, based on standard physics, that stars farther from a galaxy's center should orbit more slowly than stars closer in, the same basic pattern you see with planets orbiting our sun. Instead, she found that stars far out at the edges of these galaxies were orbiting just as fast as stars much closer to the center, a finding that made no sense under the standard understanding of gravity, unless these galaxies contained vastly more mass than what could actually be seen in the form of stars and glowing gas. That discrepancy became one of the most important pieces of observational evidence supporting the existence of dark matter, an invisible form of matter that doesn't emit, absorb, or reflect light, but whose gravitational influence is nonetheless detectable through exactly the kind of careful, patient, systematic astronomical measurement Rubin herself pioneered. It's a genuinely fitting tribute that the observatory bearing her name is now positioned to extend that exact same line of investigation dramatically further, using tools and data volumes Rubin herself could scarcely have imagined during her own working career. It's also worth digging a little deeper into how gravitational lensing, the primary technique Rubin Observatory will use to map dark matter, actually works, because it's a genuinely elegant piece of physics in its own right. Massive objects, whether visible matter like stars and galaxies or invisible dark matter, warp the surrounding fabric of space itself, a direct consequence of Einstein's general theory of relativity. When light from a distant background galaxy happens to pass near a massive foreground concentration of matter on its long journey toward Earth, that warped space bends the light's path slightly, causing the background galaxy to appear subtly distorted, stretched, smeared, or in more extreme cases, even duplicated into multiple visible images, depending on the exact alignment and the mass involved. By carefully measuring these subtle distortions across enormous numbers of background galaxies, and doing so consistently across a huge swath of sky, astronomers can essentially reconstruct a detailed map of exactly how much mass, including the invisible dark matter component, is distributed throughout the foreground regions responsible for the lensing effect, without ever needing to directly detect the dark matter itself. Rubin Observatory's combination of extraordinarily wide sky coverage and its ability to image such an enormous number of background galaxies is precisely what makes it such a powerful tool for this specific kind of measurement, since the statistical reliability of gravitational lensing maps improves substantially as the number of measured background galaxies increases, and Rubin is positioned to provide that kind of galaxy count at a scale no previous survey has approached. There's also a fascinating and genuinely underappreciated technical challenge worth understanding, one that explains why building a telescope capable of this specific combination of capabilities took roughly 2 decades of sustained engineering effort, rather than something that could have been assembled more quickly. Most large, powerful telescopes historically have had to make a fundamental trade-off between depth, how faint and distant an object they can detect, and field of view, how much sky they can capture in a single image. Telescopes optimized for extreme depth, capable of detecting the faintest, most distant galaxies in the universe, have traditionally needed to use narrow, tightly focused fields of view to concentrate enough light-gathering power on a small patch of sky. Telescopes built for wide-field surveys, by contrast, have traditionally sacrificed some of that depth in exchange for covering much larger areas of sky more quickly. Rubin Observatory's specific optical design, involving 3 separate mirrors working together in an unusual and technically demanding configuration, along with the sheer size and sensitivity of its camera, was specifically engineered to break this traditional trade-off, delivering both an unusually wide field of view and genuinely impressive depth simultaneously, precisely the combination needed to conduct a survey ambitious enough to catalog billions of individual astronomical objects, while still detecting exceptionally faint, distant phenomena like gravitational lensing effects or early-stage supernovae within a single unified observing program. It's worth spending a bit more time as well on the sheer scale of the data infrastructure challenge this observatory represents, because it's arguably just as significant an engineering achievement as the telescope and camera themselves. Processing roughly 1,000 images every single night, each one containing enormous amounts of raw pixel data, comparing each new image automatically against a continuously updated template built from all prior observations, and issuing real-time alerts within minutes whenever something changes, requires an entirely dedicated, purpose-built data processing pipeline capable of handling volumes of information that would have been genuinely unthinkable for astronomical software even a decade or 2 earlier. This pipeline relies heavily on machine learning and automated classification systems specifically trained to distinguish between genuinely interesting astronomical events, a new supernova, a moving asteroid, a variable star-changing brightness, and the enormous amount of mundane, uninteresting noise and false signals that inevitably show up across such a massive, continuously updating dataset. Building and refining that automated detection and classification system has been just as central to the observatory's decades-long development process as the physical telescope and camera hardware. And it's precisely why partnerships with citizen science platforms like Zooniverse matter so much practically, not just as an educational outreach gesture, but as a genuine, necessary supplement to automated systems that, however sophisticated, still benefit enormously from human judgment when it comes to correctly classifying genuinely ambiguous or unusual cases. Pulling all of this together, what actually happened and what continues happening right now as Rubin Observatory carries out its historic 10-year survey represents one of the most genuinely significant developments in the entire history of observational astronomy, a telescope built specifically to transform how humanity studies the universe, shifting from a long tradition of carefully chosen, individually captured snapshots towards something closer to a continuous, dynamic record of the sky's every meaningful change over an entire decade. That's a real, substantial, still unfolding scientific story, one that will likely keep generating genuine, significant discoveries about dark matter, dark energy, hazardous asteroids, and exploding stars for years to come as the survey continues collecting data night after night from its perch high in the Chilean Andes. It earned the world's attention honestly back in June of 2025, and it continues earning that attention today in the ongoing, less flashy, but genuinely more important work of steadily, patiently mapping the universe in far greater depth and detail than any telescope before it ever could. And maybe that's the most fitting way to close this out. The real Vera Rubin story was never about a single, sudden moment, no matter how dramatic that first light release genuinely was. It was, and remains, about patience, about a 2-decade construction effort, about a namesake who spent her career carefully measuring galaxy rotation until the data itself forced open a new understanding of the universe, and about a telescope now doing the same thing at a scale she could barely have dreamed of, one image, one night, one galaxy at a time, for 10 straight years. No headline needs to shout that it stopped the world. Given enough time, it just might. There's one more thing worth sitting with before we close, because it speaks to why patience, of all things, might be the most radical part of this entire project. Almost every major scientific instrument built over the past century has been designed around a specific question, a particular hypothesis to test, a narrow slice of the sky to examine in exhaustive detail. Rubin Observatory was deliberately built to do something different, to observe broadly and repeatedly without knowing in advance exactly what it might find, trusting that a decade of consistent, wide-field, repeated observation will surface discoveries nobody could have specifically predicted or designed an experiment around in the first place. That's a genuinely different philosophy of how to do astronomy, closer to building a comprehensive historical record of the sky than to running a single targeted experiment. And it's exactly the kind of approach that tends to produce the most genuinely surprising discoveries, the ones nobody thought to look for because nobody yet knew they were there to be found. Vera Rubin's own career, built on carefully, patiently gathering data until an unexpected pattern emerged from it, is a fitting blueprint for exactly that kind of science. And the observatory named after her is now positioned to run that same basic approach at a scale spanning the entire visible southern sky every few nights for the next 10 years. Whatever it eventually finds, and given the sheer volume of data involved, it's a near certainty that some of it will be genuinely unexpected, that discovery likely won't arrive in a single headline moment either. It will arrive the same way Vera Rubin's own breakthrough did, quietly, cumulatively, one careful measurement at a time, until enough of them stack up that the universe simply can't be explained any other way.